Now we will study the mechanism of radio wave banding by the ionosphere. Means how the mechanism of radio wave is taking place in the ionospheric region. How these radio waves are propagating in the ionospheric region, that we will understand here. So the whole phenomenon is occurring in two parts. First one is that the radio wave propagation through the ionosphere, where the reflection process is taking place, and in the second part there is a banding of the radio wave by the ionosphere, where the refraction process is taking place. So for the better understanding, I am sharing a image where you can see the whole mechanism, means how the whole mechanism is taking place. If you see here in the image, there is given a sky wave propagation mechanism, and the sky wave mechanism, this sky wave propagation is limited within the skip distance. So what do we mean by skip distance? It is a minimum distance from where the transmitter at which a sky wave of a given frequency is returned to the earth by the ionosphere. Here we have given these blue lines. These are representing the layers of ionosphere. As you can see, the first layer is representing a D layer, this one, and the next one is representing E, and this one is F1 and F2 layer. The whole mechanism is taking place in two phenomenon. First one is reflection, that is from here. Second one is the refraction process, and the last one is also a reflection, which is mainly due to the total internal reflection. If you can see, in this part the reflection is taking place. These layers are treating as the denser medium. So whenever we go from rarer to denser medium, the radio wave is bending towards the normal, which means it is deviating from the normal. And as we move from denser to rarer medium, we find that the radio wave is moving away from the normal. And this is what the Snell's law states. For more understanding, I am sharing the second image. Here you can see that up to here the process of reflection is taking place. Now when we move from rarer to denser medium, means from this region, whatever the region is, up to the ionized region, then we find that there is a banding of waves taking place, and a point will reach where the radio wave become parallel to the earth's surface. This 90 degree, this is showing that the refractive angle become 90 degree, and here the wave no longer refracted but reflect back to the earth's surface, like in this way. Here also we have given the skip distance. It is also called the skip zone, which consists of ground wave range along with the dead zone, and the whole ionospheric propagation, that is sky wave propagation, is taking place in this distance only, and beyond that there is no sky wave communication. Here you can also see that these waves are representing that those waves which are penetrated beyond the ionospheric region, and these wave is representing that it reached to the transmitter, and this one is showing to the critical frequency that we will study it in the next slide. So as I said, the whole phenomenon is taking place in two parts. First one is the propagation of the radio wave through the ionosphere, where we are not considering the magnetic fields. And in the next, that is the radio wave banding, here we are considering the magnetic fields. If we see the ionosphere, it basically consists of plasma which is produced by the photoionization. Basically, it is due to the photoionization where we find the presence of positive and negative electron. The plasma is representing the positive and the negative ions that get charged when it comes to the contact to the solar light, and there is some motion occurs in them. So we can say that the ionospheric region consists of plasma which is produced by the photoionization of a thin upper atmospheric gases by the UV rays, that is ultraviolet rays, and the photons of short wavelength from the sun. You know, this distribution and the dynamics of the plasma is independent on the coupling between the neutral atmospheric winds, solar heating, photoionization, electrical conductivity, and the interaction with the magnetic field of the earth. So if we look the whole mechanism, the bending of the radio wave at the ionosphere can be readily be understood with the help of the refractive index formula of the ionized region. If you see, this is the formula we have given. Here, mu is the refractive index, and n is the ionic density in the meter per cube, and f is the frequency which is representing in hertz. So, in the practical situation, if we see in the practical condition, in the practical condition, we have find that the value of mu is always less than unity. Means if f square is less than 81, then it will represent that the refractive index become imaginary, which means under such condition the radio waves are attenuated at the frequency, and the ionosphere is not able to transmit or band the radio waves. Now, if we see the banding of radio waves, then we find that it follows the Snell's law, according to which mu is equals to sine I by sine R. So whenever the light travel or the rays travel from the denser to rarer medium, it bends away from the normal. So as we seen that we have mu less than 1 for the ionosphere, so our sin I will become less than sin r. That means that the angle of refraction will go on decreasing, or sorry, deviating from the normal as the wave will encounter rarer medium. And if we see, there is a relation between mu and m. You know, mu represents the refractive index, which shows the deviation in the radio wave, and as the mu increases, ionic density, that is electron density, decreases. There is an inverse relation in that. As we go up to the height, when mu is less than 1, so whenever we go up to the height by means, I mean that whenever we go from D layer to F1 layer, E layer, F2 layer, we find that our mu is decreasing, and it is decreasing and decreasing. So we can conclude if the successive layers of the ionosphere are of higher electron densities like n6 greater than n5 greater than n4, that we have given the condition, that is greater than n3 greater than n4 greater than n1, it means that our mu, which is refractive index, which it will go on decreasing in the way mu1 greater than up to mu6. Thus a wave Thus, a wave enters at a point, we can say a point P, and it will deviate more and more, and a point will reach where it travels to the where the wave will travel parallel to the Earth's surface, which means a refractive index will become 90 degree. So, in that condition, if we see, we can find that our mu m will become sine I. If we take mu m be the refractive index and nm be the maximum electron density at the point of pm. Pm is the point where the refractive index is becoming 90 degree, and the total internal reflection is taking place, where the wave is no longer refracting from the path but reflect back from the ionized region to the earth's surface. And now, if this condition is fulfilled, so we can conclude that the radio wave, once entered at a point P, it will leave the ionosphere at a point after the slight penetration into the ionosphere, and thus the radio wave are reflected back to the earth after the successive refraction in the ionosphere. So this is the whole process or mechanism going on. Like, now coming to the next topic, that is a critical frequency. The critical frequency of an ionized region of the ionosphere is defined as the highest frequency which can be reflected by a particular layer at a vertical incidence. By the vertical incidence, we mean that the angle of incidence is 0, and the highest frequency is called the critical frequency for the particular layer. So it is specific, the critical frequency is specific for the specific layer, as we already discussed in the ionized region, that we have D layer, E layer, tropospheric region, and F1 and F2. So they have their own critical frequency that varies from 100 kilohertz to 30 or above megahertz. So, so we can also say that the critical frequency for a particular regular layer is proportional to the square root of maximum of electron density in the layer. If we see the formula, means we can also say that it is different for the different layers, and it is denoted by F naught and Fc. Now if we see that the critical frequency is directly proportional to the square root of maximum of electron density in the way, like we have given mu is equals to sin I by sin r. So as the condition of critical frequency is I is equals to 0 and n should be maximum, that the electron density, if it is maximum, then F will become the critical frequency. As the angle of incidence go on decreasing and reaches to 0, so we can say the electron density go on increasing, right? Because it is inversely proportional to it, and reaches to the maximum electron density, that is Nm, and the highest frequency that can be reflected back by the ionosphere is the one for which the refractive index mu becomes 0, as shown in the condition. In this, the whole mu is becoming 0. So from here we find, so here we find the MUF, which is the usable frequency. It is a frequency, it is a frequency that can be reflected from the layer and is a function of angle of incidence. Wait. So MUF is the usable frequency which reaches to the earth after the reflection. Now, all in all, we can conclude that this is the condition that we have given. So we can conclude that the critical frequency gives an idea that the radio waves of the frequency equal to or less than the critical frequency will certainly be reflected back by the ionospheric layer irrespective of the angle of incidence. So we are mainly focusing on the refractive index, so we can conclude that it is not the means the reflection is not dependent on the angle of incidence, and the radio wave of frequency greater than critical frequency will also be returned to the earth only when the angle of incidence is sufficiently glancing or satisfied at the frequency involved. Otherwise, what will happen? The wave will penetrate through the layer. So we have seen all the condition of it. So this is what the whole mechanism of the radio wave banding by the ionosphere. Now moving to the next slide, we have covered the advantage of the sky wave propagation and the disadvantage also, along with the application of it. If we see advantages are that it supports for the large distance propagation. It is used for the long distance propagation, right? And if we see the frequency of operation, then it is considerably high, because as we already know that it works from the range of 3 kilohertz to 30 gigahertz, 300 gigahertz. So we can say yes, it is considerably used. It uses a large range of frequency, right? And attenuation due to atmospheric conditions less. As we have seen that in the ground and the space wave there is a possibility of attenuation, but when we study about the ionospheric region, then we find that there is a less possibility of attenuation. If we see the disadvantage of it, then we find that the long distance propagation requires a large size of antenna. As we already know that the frequency and the wavelength relation is inversely proportional to each other, and the wavelength is is depict the wavelength depicts the height of the antenna. So larger the wavelength, larger be the height of the antenna for the good communication. So it is one of the disadvantage that if we are using the high wavelength and if we are using the antenna for the long distance propagation, then a we need to use a large size antenna. Second point, we have given that due to the presence of ionospheric near and far during night and day respectively, there exists variation in the signal transmission in the day and the night. Yes, because in the ionospheric region the refractive index varies along the as we move up, to the layers of the ionospheric region, so we find there is a deviation in the signal. So this is one of the disadvantage of that. And in the night time, what will happen, the as we said that the f1 and f2 layer will combine and the d layer vanishes. So we can say that it ultimately affect the quality of signal. Application, we can say that along with the broadcasting purpose, it is also used for the mobile and the satellite communication, and for the atmospheric conditions too. I hope i hope everyone has understood the mechanism of radio wave banding, and this video come out to be as helpful one. Thank you.